the probability that, and you replace those words with the P question. Right? So in this particular problem, I'll read it again. It says, when 4,000 automobile engines are produced, on average 10 are found to be defective. A random sample of 80 engines is selected. What's the question? How many defective engines do we expect? And how do you answer that? I mean, and Jennifer just said it correctly, but for the rest of you, how do you answer this question? Yeah, what am I writing? 10 over 4,000 equals lambda over 80. You said that as a proportion. So if you had 10 defectives out of 4,000 engines, how many defectives do you expect to get in 80 engines? That's the question. And solving this is not too difficult. We're going to have to multiply both sides by 80, and we get lambda equals 80 times 10 or 400, which is 0.24. Okay, what's that? Yeah, and the question says, find the probability that none are defective, and so x is 0. And now, what do we do? Table C. Okay, look at table C. Work that out on your calculator.
Yeah.
Can you say what you did again? I'm curious.
Okay. I did 1 minus, in parentheses, 1 over 400 squared times, sorry. I did, yeah.
You used the 80 in there somewhere, right?
Yeah, that was the second part. I did 399 over 400, 280.
Then just make sure you write the word Poisson, and I think you're in good shape. You know what I mean? If you're able to do it, ultimately, I shouldn't say that so. I should be write the name. Show a clear method. So what I don't want to see, and I sometimes do see on papers, is like this. And then I get an answer in here, you know, and they say, "Oh, work was there. Look at the corner; it's right there." And I say, "I can't read all of that, you know. I want to see a clear set of steps." So if you can show it, even if it's not the way I showed you, if it's logical and if it can be explained, yeah, that's fine.
So like for this example, I mean, when you want to find, basically it's just like a series of decisions, right? You want to find. First is not defective, second is not defective, third is not defective, and the fourth is not defective.
The question is that none are defective, right? And you've got 80 engines. So, I mean, it's going to take you a very long time to write it out like that.
Well, right, but I mean, couldn't you just put it to the 80? all you're doing, you're taking that probability, multiplying it 80 times.
The only reason it worked in this case is because I said none are defective. If I had said one are defective or two are defective, then you got to work out all the orders of which two could be defective. And then it gets really messy really fast. So, as a general method, it probably is not going to work. Okay. So we're good on part A, right? Okay, how long should part A take you?
2 minutes.
2 minutes, that's fair, right? We agree? That's about a 2-minute question. Not 20. Okay, because right, you got an hour and a half test, you got the budget time. So, yeah, quick question.
Oh, go ahead.
Sure.
Why is 90 over 80 the same as the average for the other information?
Why is this?
Why is that average the same as that one?
Well, let's just suppose, picture that I have 4,000, we'll picture they're little engines. I got 4,000 little engines of them. And I've got, out of those 4,000 of them, 10 of them are defective. Okay, that's what we're saying. So not that many. I mean, only really 1 out of every 400 engines is defective. So now I'm going to take that same group of engines, and I'm going to pick 80 of them, randomly pick 80 of those. So I have 80 engines. And I want to know, out of these 80 engines, how many of these do I expect to be defective? And many students will say, well, 10. And that doesn't make a whole lot of sense, right? If there's 10 defectives out of 4,000, there's not going to be 10 defectives, probably not out of 80. Probably be pretty small. And it works out, proportionally, you can see it works out to less than 1. And your point 2 is the expected number of defectives out of the smaller amount of 80.
So you kind of like apply the same average to a smaller scale.
Yeah, it's a smaller scale, the same thing.
The same, it's the same thing.
Right.
Is that how you're always going to find the lambda?
Yeah, lambda. Yeah, that's how you do it. Lambda?
Yeah.
Sometimes this can be a 1, and that makes it easier. And I did give you a question early on where it was really easy to find lambda, which is almost misleading because it's not easy like that. This is more typical.
What if you did you used the E, like how would that?
Oh yeah, you can. You could do it with the formula, and it's funny because a lot of students that have given this question will do the formula. Unlike I joked around with you, it's just because they didn't write down their notes that the table was there for them to use. But it's okay, you can get it that way. And you would say e to the lambda is 0.2, so e to the negative 0.2 times the negative 0. Not negative, just positive. 0.2 to the x, which would be 0.2 to the 0 over 0 factorial. And this is a 1, and that's a 1. This works out to be e to the negative 0.2, and you have to work it out in your calculator, and it should be the same answer.
Why is it 400?
All right. One of those mysteries in life. Okay, thank you. Other questions?
So what does lambda represent?
Lambda represents the mean number of occurrences for a specific group. So in that example again, we knew that 4,000 engines, out of 4,000 engines, there were 10 defectives. Lambda represents the number of defectives that we expect to get in 80 engines. So you always have to take into consideration your new number. You have 80 engines, not 4,000 anymore. What is the expected amount for that smaller amount?
So that's 1, 2.
And that's 0.2.
And then why is the x 0?
Well, because the question said find the probability none are defective. So 0.
So
And if I asked you for the expected number, actually, that's here, so I won't jump ahead. Let's do B. Find the probability that more than 2 are defective. What are we going to do? What is X now?
0, 1, 4, 2. Oh,
Yeah, you know what I find on this next test? I've seen this over and over. That students, they get their notes looking great, they practice the questions, they know how to use the tables, and then I give questions like more than 2 and they read less than 2. Or they read it at least 2. Or they read exactly 2. And it's like, after all the work
wrong to write x as x equals 1 minus
0, 1, and 2.
0, 1, and 2?
That might be a really good idea. Yeah, so what we could say then is we could say, well, if x is 3, 4, 5, etc., we might want to use the complement
Yeah.
and say, well, that's equal to 1 minus the probability that, and do we include 0 here?
Yes.
Yes, that is a possibility. So 0, 1, or 2. And that's a good way to work this thing out. We have obviously fewer to work out. Now, you especially want to do that if you were working out this way, because doing this with this is a nightmare. But, but we have the table, so it doesn't even, we can just work it out easily by looking at the table. And what do you find using the table?
0.8187, 0.1637, 0.0164.
4.
That's it.
0.0164.
Do you know, if you have the table in front of you and look at it, do you notice anything interesting about our decision of using the complement? What I'm saying won't make sense unless you see it on the table. So stare at the Poisson table C, and then now let's go back and evaluate the decision that we made to use the complement in this problem.
It's really easy. It's really easy.
Which way is easy?
Just adding up the 0, 1, and 2.
It's actually easier without. Because typically doing the complement is exactly what you would want to do in a problem like this. That's typically what we would say. It just turns out with this particular problem, it makes it harder. Why? Well, because the table, if you notice, here, I've got it showing here. You get these sort of bigger numbers to start, and then by the time you get to 3, it's the really simple number. You're just adding 0.0011, 0.0001, and the rest are just, they round to 0. So this answer is just 0.0012, and we're done. If I had done it this way, it would still get the right answer, but I would have to do the work of writing out those first 3 numbers and subtracting them from 1.
Makes sense. You lost me.
Yeah.
So see here.
In the geometric,
So for more than 3, for 0.2 as a lambda,
Right.
there's only 2. This
Okay.
0.0011 and 0.2.
If this was a
Which equals a
geometric
0.0012. Same thing of adding up all
we
this.
would have no choice
minus
first
1.
of all, because there's no table to help us.
Same thing.
We would have had to use the complement, and we would have left out the 0 if it was geometric. Why? Well, because it's the type of question it is. This question that you have to say, is it possible that there could be no defective engines? Yes. It is possible you have 0 defective engines. So 0 is a possibility. If you go to a geometric where I'm going to roll a die until I get a 6, is it possible that it takes me 0 rolls to get a 6? No. So you have to start that with a 1. That's why it's big question. Do we see why the answer is 0.0012?
Yes.
Let's answer part C. It says find e of x and variance of x.